Welcome to the last session of the day. This is the Best of CCR session in which two of the best papers that have been published in SIGCOMM's flagship newsletter, Computer Communication Review, are presented to you. We have two excellent papers. Our first will be presented by Loqman Salamatian, which I hope, who is a fourth-year PhD candidate at Columbia. He is interested in measuring the internet to model the relationship between the virtual and geographical spaces. And his talk is called, Who Squats the IPv4 Space? And so welcome, Loqman.
Thank you. Let me tell you a story. I once received a call from a friend in distress sharing a trace route and asking me why their traffic was getting routed by the DoD. After a quick Google search to try to understand what was happening, I found many posts of users mentioning something similar, that their first hop in their trace route measurement belonged to the Department of Defense of the United States, or that their cellular network was being routed through interfaces that were allocated to the UK Ministry of Defense, or even worse, that their Windows update were directly installed from the DoD. Could they have been under the surveillance of a government that was tracking their every movement on the internet without their knowledge? And if so, could you have been? Luckily, reality is less dystopian than a George Orwell novel. The most likely explanation for what my friend and those users have been experiencing is that their ISP and CDN are squatting IP addresses. To paraphrase the RFC, squatting is the idea of using someone else's unannounced IP address space to configure your own network. Squatting fits into that larger context of solution that extended the IPv4 shelf life. NAT and carrier-grade NAT were initially introduced to mitigate the IPv4 scarcity by allowing the utilization of a dedicated pool of private and reusable address space for certain applications. And while that allowed to relieve the tension on IPv4, the internet has since witnessed an incredible surge of demand for IP addresses from all kinds of organizations. Cloud providers, for example, have scaled up their operation, requiring more addresses to configure their virtual services. Similarly, access networks have to accommodate an ever-growing number of devices and internet users. Many networks and applications are also not ready to move to IPv6 or require dual stack. In this context, the pool of available private and public addresses just isn't sufficient to keep up. This sets the stage for IP squatting to emerge as a viable solution. The key observation that makes IPv4 squatting possible is the following. More than 20% of the IPv4 address space has largely remained unannounced since its allocation in the 90s. We call squat space all of the /8s that have been historically unannounced. The organizations who own the squat space are predominantly early pioneers of the internet who got their /8s in the 90s. The DoD in particular holds a commanding presence, owning over 60% of the squat space. Since squatting consists of using IPv4 addresses that have historically not been advertised to the network, one might wonder if IPv4 squatting is really bad. We answer this question following three axes in our paper. As I highlighted at the beginning of this talk, my friend was confused by the presence of a government so close to their home router. So that's not great. Squat space also distorts our view as researchers. When we inspected datasets that are widely used by networking researchers, we identified many instances where the presence of a squatted address was leading us to incorrectly infer links between the Department of Defense and an organization that was simply squatting. Similarly, we found many instances where the geolocation was incorrectly inferred. Even worse than that, squat space can get reclaimed and announced by the legitimate owner to the internet. When this happens, many things can go wrong. Let's assume a scenario where an AES is squatting an IP address from the DoD, and the DoD decides to start announcing this /8 legitimately. We imagine two kinds of behaviors. In the first scenario, the internet users try to access the DoD IP address and gets routed toward the squatted device, suggesting that the internal route is privileged over the external one. In that case, the user in the squatting network is unable to reach the legitimate owner of the address. You can also have the opposite scenario, where the external route gets privileged instead of the internal one. In that case, the device using the squat address might become unreachable, Both of those instances can break the internet. Finally, squatting opened a lot of interesting legal questions. An FBI talk took the stance to consider it a prosecutable offense under certain circumstances. However, there is no legal precedent. Given the limited insight available in the law literature, we decided to partner with the Harvard Cyber Law Clinic to delve deeper into the nuances of IPv4 squatting. They've documented an analysis leveraging legal first principle in a detailed memo, which we cite and link to our paper. Feel free to check it out if you're interested. To identify squatting in the wild, we use multiple traceroute dataset. Squat addresses are usually used internally to network, and so aren't generally reachable from outside the network. So to get broad coverage and a rich understanding of the use of squat, we needed to be able to measure routes from many networks. Existing research platforms like RIPE-Atlas and Kaida-Arc are widely used measurement platforms, but they have very limited source coverage relative to the size of the internet. What really enabled our study of squat space was the Audin dataset. This dataset, sourced from Microsoft customers, offers a unique visibility into the internal topology of users worldwide and consists of traceroute toward Microsoft for most network and prefix hosting end users. Now let's go back to our original traceroute and try to identify who is responsible for the squat. If we use standard IP2AS or IP2org mapping, we'd incorrectly label that IP address as belonging to the Department of Defense. So we need to come up with something slightly different. Our main idea can be summarized as follows. We first insert the client IP address observed by Microsoft Server as the first hop. We then map non-squat IP addresses to ASs using standard techniques. If a traceroute includes a contiguous sequence of hop with squat space and private IP addresses surrounded by a public IP address mapped to the same organization, we attribute the squat usage to that organization. So for example here, the responsible of the squat is Columbia University. We discuss more complicated example in our paper if you're interested, but that gives a gist of how we do the attribution in practice. After talking with some network operators, we realized that in some instances, the providers were not responsible for the configuration. It was just a rogue user using squat space. For example, in that instance, our lab used squat addresses for experiment without oversight from Columbia, and the reason why we did that is because we exhausted all of our private IP addresses on IoT devices. This pushed us to develop a methodology that allows us to distinguish who is responsible for squatting between the provider and its customer, and how the IP address was being used concretely. In the interest of time, I will not dive into the details of how we do that, but that's all in the paper if you're interested. I move now to the results section. Our primary finding reveals that squatting is widespread among organizations. In total, we've observed over 2,900 organizations involved in squatting. When we categorize this organization by type, it becomes clear that squatting is a common behavior across all types of organizations of the internet. Regarding the question of how were squatted IP address used, we first examined internal and border routers. We found that squat addresses are rarely used for border routers and are more frequently used for internal routers, in particular for access in large transit networks. We also observed that squat spaces are commonly employed to configure diverse NAT, and this was something that was already observed in prior effort that focused on understanding NATs and carrier-grade NATs. In particular, squat space usage can be linked to a customer NAT, suggesting that a handful of customers might be primarily responsible for the squatting in that organization, or into a carrier-grade NAT, hinting at the fact that the providers are the one driving the utilization of the squat space. I now move to the analysis of the geography of the squatters. On this map, we color the countries based on the number of squatting organizations that we found registered in that country. The US and Brazil top the list for squatting occurrences, but it's important to remember that they also have the highest number of registered ASs. The number of squatters in the US, for example, is simplified by the substantial presence of cloud providers, tier ones, and those are organizations that usually require a lot of IP addresses to be configured properly. The region with the highest number of squatters, more than 800 organizations, is the APNIC region. APNIC was the first registry to exhaust its IPv4 addresses in April 2011, and has had since the growth of internet users. So the fact that squatting appears as a solution there does not strike as a big surprise. We saw that squatting was widely spread and that all kinds of organizations might be squatting. So it's important to understand what happens when the space gets reclaimed. In January 2021, a really interesting change occurred. The DoD started announcing its unused IPv4 address space. This move brought squatting into the spotlight because of its timing, happening minutes before Donald Trump's departure from office. There is probably no relationship, by the way. It gave us the unique opportunity to understand the effect when squat space gets reclaimed by its legitimate owner. For this talk, I will highlight only two aspects of interest. First, we wanted to know if operator would stop squatting now that the address was being officially used and advertised to the network. Only 30% of the ASs that we were measuring decided to play fair and halt squatting. And we imagined that for those 30%, updating the network to stop squatting must have been a headache, because it required changing a lot of configuration. But here is an even more surprising twist. After the DoD announcement, we started observing ASs squatting for the first time the DoD address space. We don't have an understanding of why this happened, and we're interested in understanding it. So if you know, please talk to me at the end. Finally, we mentioned it earlier, but when squat space gets announced legitimately, we can observe a fragmentation of the network. And so we were curious to see what was happening in practice. Out of the 497 ASs squatting and hosting measurement device that allow us to run traceroute, we noticed that when we were triggering a measurement toward the newly now reclaimed DoD space, 57 privileged the internal route, 307 privileged the external route toward the DoD, with the traceroute being unresponsive from Ashburn onwards, and 46 exhibited both behavior depending on the source and the destination IP address, hinting at a real fragmentation of routing behavior even within the AS. In conclusion, in this talk, I showed that squatting is a very commonly used way to work around IPv4 depletion, that we as researchers have not acknowledged squatting in any way in our topology measurement, and that we should carefully consider the impact of squatting on future study and maybe revisit old ones. And finally, that squatting opens up a lot of interesting legal implication, and that there is currently a void in how those cases should be addressed. This effort will be highly multidisciplinary, and if you're interested in participating in that conversation, please find me. I'm happy to talk about all of this. Thank you for your attention. I'll take any question now.
Thank you, Loqman. Great hometown crowd. Awesome. Any questions for Loqman? Anybody want to squat on the question time? Okay.
Thanks. Hi, I'm Julian from UC Berkeley. I was wondering, do you guys know how many false positives you got, in particular for the border squatting? I feel like there's probably a hard test to know if it's actually squatting or if it's just the natural flow.
So for border routers, we come up with a solution that allows us to do this inference, and we describe it in the paper. I wouldn't be able to tell you how many false positives we have. I mean, for a false positive to exist, I believe you would need to have an interconnection between the DoD and this AS. And this is not something we have looked too much in detail, but I will take a deeper look, and I might be able to give you an answer by tomorrow, for example.
Oh, thank you. I'm curious if
You're Henning.
Yes, I'm sorry, I didn't get. I'm curious if anybody has ever tried to sue anybody for that type of. You mentioned it in the last area, and related to that, have you tried to reach any of these squatting entities to the extent that they were legitimate sounding? I mean, like university or a carrier or something that, as in, was this seen as kind of a victimless crime, as in nobody's really using it, so I'm squatting on it, type of thing, but the DoD isn't really doing anything anyway, type of deal? Or was it like, yeah, we know, don't talk to us about it because this is sensitive type of thing, or you never got an answer at all because whatever?
This is one of the feedback we received on the first submission of that paper. It was, how about doing a survey? And we thought about it deeply. We did reach out to a few contacts we had, but we had some trust So we knew that we could ask them that kind of question and they would answer honestly and tell us, well, we are not responsible for that usage versus we are, and we have an agreement with the entity we're squatting. One of the reasons why we didn't decide to do a long survey is because we thought that there is no incentive to be honest. In that instance, you're doing something that is frowned upon, where there could be potentially implications because the FBI mentioned in one talk that it could potentially be prosecuted. So there is no clear incentive, and we don't have the right skill set to do those kind of survey. But we are interested in doing that, but we need someone that is knowledgeable in how you can generate those kind of survey and handle the data in an appropriate manner.
One more question.
Hi, this is Oliver Gasser from MPI for Informatics. So in the beginning of your talk, you mentioned that companies might squat IP address space because they were not yet ready to move to IPv6. Did you look into this at all? Are those companies who squat IP address space not using IPv6 at all?
So we didn't look at this in detail. I would say that we guessed more than we did a thorough study, that there are some applications that are just not IPv6 friendly, and so maybe there are some organizations that don't want to do this move into IPv6. Another thing is, a lot of the ASs that are squatting nowadays are ASs in regions where you might not have the proper training to do this transition to IPv6, and so there is a kind of a tension on, having IPv6 deployed in certain part of the world. So I believe that there is a relationship there, but this would be really interesting to study more in detail and have an in-depth study of how often that correlates.
Great, thank you. Excellent.
Thank you.
Okay. Next up. Sorry about this. Next up, we have the packet number space debate in Multipath QUIC. This will be presented to us by Quentin de Coninck, who just became an assistant professor at the University of Mons in Belgium 10 days ago, where he focuses on computer security. Congratulations. He was a student and a postdoc at the UC Louvain in Belgium, where he studied Multipath QUIC, which he's also standardizing. So, Quentin.
Yeah, so...
One more time.
You can duplicate. Thanks. Yeah, that's better. So thanks for the introduction. So as the title says, it will focus on Multipath QUIC. So a quick reminder first. So it's a new transport protocol that provides reliable and encrypted services atop UDP. And packets look like this. So you have a very short-lived text header with small flags and a destination connection ID that allows endpoints to map packets to their connection. So you are not bound to the 4 tuple anymore, like in TCP. And then in the encrypted part, you have a monotonically increasing packet number that allows you precise recovery. And then you have a sequence of control data frames that are the core messages in QUIC. And so you can have different messages, such as the ACK frame to acknowledge the packets, new connection ID to provide alternate connection IDs, and the stream frame to carry the data. And one of the main features that you have in QUIC is connection migration, which means that you might have one mobile device, you may be on the Wi-Fi, you do some exchange on the Wi-Fi, and then you may lose Wi-Fi connectivity. Instead of losing and breaking the connectivity, you can migrate the connection to another network path, because you have different connection ID, so the server can map it, and the server will just follow the new path that is used by the client to send then its responses. But as you notice, it will only follow the last path taken by the client, and it will set the congestion control and so on. So its main usage is for single path data sending. So don't expect to use it with multiple paths. It will work quite badly. And actually, to do actual multipath, there were several proposals that were proposed at the ITF, so for standardization efforts. And as of September 2021, there were 3 competing proposals, but they were considered either too complicated or too specific to their use cases. But the authors wanted to make some progress, so they focused together, so they made, in the end, a common proposal that focused on the common core multipath mechanism that you should have. But besides the fact that we agree on a lot of elements on a multipath, there remains one main design question that remains answered, is the number of how we are going to number the packets in multipath QUIC. And there were two main proposals. So the first one is to have a single packet number space, like in single path QUIC, where you just say, OK, I have 0, 1, 2, 3, 4, 5, and I will just send 1, 2, 3 on one path, 4, 5, 6 on another path. And the sender just keeps track on where it has sent the packet, and the receiver just discovers when they arrive on which packet, on which path it received the packets. And it has the advantage that you can just still rely on the regular ACK frame. And another design that we propose is to have multiple packet number spaces. So you need to have different connection IDs on different paths. And the idea is to associate a packet number space on each connection ID. And so you can have a contiguous packet number space on each path like this. And because now you have multiple 0, 1, 2 over a given connection, you need additional means to when you acknowledge a packet, which packet number space you acknowledge. And so you have a new frame, which is called the ACK frame, that contains the identifier of the path you acknowledge. And there was a lot of discussion just for this. And there were basically two main arguments. So the main argument for single packet number space, you say we have less changes in the code. So let's do that. And the main argument for multiple packet number space is it's cleaner. And you do not need to change a lot of your recovery. And the point we are focusing now is you do not bother about how the receiver handles the acknowledgement state. And to understand why this is important, let's focus on single path QUIC and how it acknowledges packets. So let's assume we are at the beginning of the connection, and you receive 3 packets, 0, 1, 3. What the receiver does, it keeps track of the range it has received. So it will here have 2 ranges, so 0 to 1, and then 3. And it will send an ACK frame containing these ranges. Then you can receive additional packets that can create additional ranges, so it needs to maintain more state. But hopefully, in the end, you will have the peer that will send also an ACK frame that will acknowledge a previous packet that contain an ACK frame, which means that you can drop and prune the state that you have in the previous ACK frame, and so that's how the receiver can keep track of the ACK ranges while keeping the memory low. But that's the ideal case. Sometimes you may be in a case where you have ranges and you keep receiving packets, and these packets increase the number of ranges you need to tackle. If you do nothing, actually, you can just increase the number of ranges you need to maintain indefinitely. So what you need to do is actually implementation need to maintain a limit on the number of ACK ranges that are willing to maintain. And what they do is they have a hard limit. Let's say in that case you have a hard limit of 8 ACK ranges. And what you do is just you drop the oldest range you had. And why the oldest? Because actually beforehand, probably you have sent an ACK frame containing that range before. So that's one thing that single path QUIC implementation receiver need to do. Another thing is this one. Let's assume you are late in the connection, so you have exchanged a lot of packets, and then you receive a packet with a very low packet number at some point. But in the meantime, you have pruned your ACK range, you have pruned your ACK state, and the question is, did you already receive that packet? Should you process it, or should you discard it? And the point is that the implementation needs to keep a minimum packet number below which they consider all packets as duplicate to prevent some kind of attacks that you may have. And you can have different implementation of this. You can be latency-based, but many production implementations rely on a fixed threshold based on the packet number, which is the largest packet number that you have received minus some constant, which is typically 127. And now that you have seen how in single path QUIC receiver handles acknowledgement, let's see how it works in multipath. And for that, we have done experiment in S3 DCE environment, and we focused on the PICO QUIC implementation, which is the one that has both support for single packet number space and multiple packet number space, and it was optimized to have good results with both. And by default, it relies on a latency-based ACK horizon and a range limit of 32. And we focus on a large bulk transfer. So we apply experimental design, where we explore a lot of different configurations on 2 path topologies, and the sum of the bandwidth and the latency that you have on both paths are always the same. Doing like this, we expect to have the same transfer time broadly for all the network scenarios that you may have. And so we compare here, and we have here the results, so the cumulative distribution function where each dot corresponds to a network scenario. And we notice that in most of the time we have similar results. Sometimes the single packet number space is a bit less good, but that's still OK. Now focus on the case where you might be very memory limited, like an IoT device, and it has a strong limit on the number of ACK ranges that it wants to sustain. In that case, if you have a range limit of 5, actually the performance drops a lot, just 5. And the reason is the following. Because in a single packet number space, when you send 1, 2, and then 3, 4, actually you are creating ranges on each pass. And you are going to receive the ranges fastest on the fast pass rather than slow pass. And so what happens is that the receiver here has all ranges coming from the fast pass, then it receives a new packet, creating a new range from the fast pass again, but it has to drop one range, so it drops the oldest one. And then it receives a packet from the slow pass, but it needs to create an additional range, but you can't create it. So what you do, you receive the packet, you process it, but you never acknowledge it. And so actually, you trigger spurious retransmission at the sender side. So we mentioned the ACK range limit, but we also mentioned the ACK horizon. And if we have a fixed ACK horizon, actually performance are quite bad as well. And the reason is quite simple. If you are late in the connection, you have high packet number, a large congestion windows, and you are sending a lot of packets on the slow pass, and then you send a very new packet on the fast pass. You have ACK horizon, which is quite low here. You receive just then the 300 packet number. You increase your ACK horizon. You only have 2 ACK ranges. That's fine. And then you receive the whole packet on slow pass. It's below your ACK horizon, so you discard it, and so it's not even processed. So the data is just dropped, and so that's bad. Just quickly to mention that we also did experiments on 3 paths, and in that case, single packet number space is very bad, and you need to increase the number of ACK range you are willing to support, depending on the network condition that you may have. So that's annoying. And so to conclude, so the protocol design is important if you want to actually make it work in a lot of situations. And from experience, doing multipath is easy, doing it right is very hard, because it depends on the sender algorithms, it depends on the network conditions, it depends on what the application wants to do. And if you add variability due to the receiver heuristics, and you make multipath unusable in specific use cases, by design, that's a bit annoying. And so actually, we brought this work back to the ITF, and we reached a consensus to only focus now on multiple packet number space. So this concludes my presentation. Thank you, and please.
For Quentin. Questions?
Hey, great talk. Jun Kim from UVA. This number is, you know, the ACK ranges and ACK horizon. I just trying to understand, like, if this is set and each client or server has their own QUIC implementation,
Yes.
Is it set and fixed, or is it dynamic? Can you change it, or?
So actually, the QUIC specification is quite complex, 300 pages, I think. And there are, I think, more than 20 implementations. And each implementation does its own heuristic. So the Pico QUIC implementation does quite very clever stuff, but you do not expect all implementation to do that. If you have one implementation that has its own heuristic, which is very simple, and that works very well on single pass QUIC, why would I change it?
Okay. Thank you.
More questions?
Hi, Gina from Stanford. Has anything like this come up before when designing multipath for other protocols like TCP, multipath, and how has that experience influenced how you're designing stuff like this, packet sequence numbering for multipath QUIC?
So that's a good question. So actually, before starting to work on Multipath QUIC, I also work on Multipath TCP. And Multipath TCP has a special case where first the numbering is based on the byte of the stream instead of a packet number where you have in QUIC. So it makes some recovery ambiguous. And Multipath TCP is both multiple packet number space and single packet number space in the sense that on each TCP path, you have just TCP sequence number, which is specific to each path. But you also have the multipath data sequence to reorder depending on the different paths, which is single path, which is shared between the different paths. And actually, we add some issue due to that number which is shared, and sometimes, in TCP, we are mainly constrained due to the fact that it's bound to the byte stream itself. In QUIC, it's so easy to just have this because it's much more natural in the sense that you have different characteristics on each path. They may have different latencies, but they also have different loss characteristics. And yeah, that is just more natural at first glance. And the advantage of having the other proposal is that now we know that it's probably better to do like this than the other one.
Any other questions? All right, I will ask one final self-indulgent question. So this is along the lines of how difficult it is to design good protocols. Are you familiar with DCCP from Kohler et al. Around 2005?
I follow a bit what they do.
Yeah. Okay, so that's clearly a worse protocol than QUIC, and yet it's still there and it's standardized. Does that hurt anybody, or should somebody like kill it? And if so,
well,
how?
Do you know how many multipath DCCP or even DCCP implementation exists?
Multipath DCCP?
Yeah, there is also multipath DCCP, which is standardized. But there is a Linux kernel patch that, but now the Linux community announced that actually they will drop DCCP. So they don't have many implementation anymore.
Good. Thank you, Quentin. Excellent work. All right, student dinner, and then tomorrow, 8:30 a.m. See y'all.